All right, welcome everybody to today's webinar with ISES. We are very pleased to have all of you here, and we welcome you to this webinar on solar forecasting and the work of the IEA PVPS Task 16. My name is Arabella. I am the Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany, and I will give you a short introduction into ISES and the work we do, as we have many new participants joining us on the webinar today. The International Solar Energy Society ISES is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ISES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISES, and you can find out more on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings, such as today's, in the ISES Webinar Archive. ISES members can also get discounts and even free registration to ISES events and partner events. Every month, ISES publishes a newsletter for our members where you can follow our progress and share your news. Members can also subscribe to our academic journal Solar Energy, our flagship publication, at a reduced price. And in the ISES online bookshop, ISES members qualify for reduced prices on the different publications. So we welcome those who are not yet members to join today to support our work. For those who are already a member, we thank you for your support. As a special benefit to all attendees of today's webinar, we are very happy to offer a special discount when signing up as an ISES member. All attendees of this webinar will receive a 20% discount code as follow-up to this webinar over the next few days. This special offer will only be valid for 2 weeks after this webinar, so sign up quickly and join ISES and the global solar community. Now some brief information on the webinar and especially the Q&A session before we start. During today's webinar, we will hear the presentations by our expert speakers, and this will be followed by a Q&A session for you, the audience. For the Q&A session, we invite you to send in your questions, and we're looking forward to your participation. When sending in the questions, please write who the question is for and keep your questions short and precise. Please feel free to start sending in your questions anytime throughout the webinar. I am now happy to introduce you to our moderator for today, Dave Renné, ISES immediate past president. Dave will present today's opening remarks, introduce our speakers, and moderate the Q&A session. Dave served as the president of the International Solar Energy Society from 2010 to 2019, and he's the current ISES board of directors. He's member of the current ISES Board of Directors, as well as the ISES immediate past president. Dave managed the solar resource assessment activities at the US International Renewable Energy Laboratory NREL, and he's dedicated to the concept of urgently achieving 100% renewable energy to meet all of our end-use energy requirements as the best solution to the climate crisis. Now, I'm happy to hand over to Dave. Dave, thank you for joining us. The floor is yours.
Thank you very much, Arabella, for your welcome, and thank you everybody for your participation in this very interesting webinar. We have an outstanding group of panelists today, and so I want to get right to the webinar, but before I do, I just have a couple of brief announcements. I think, Arabella, if you could move the slides back, there we go. One point I wanted to make is that ISES is a member of the Global Solar Council, which is the voice of the world's solar energy industry. The council was established back during the Paris Climate Conference in 2015, and ISES was a founding member of that organization, which has a mission of promoting the rapid adoption of solar energy globally through market development, partnerships, and education. So besides being a founding member and a member of the board of directors, ISES also chairs the Global Solar Council's technical committee. And this webinar is also presented, therefore, on behalf of the Global Solar Council's committee. And then one other piece of information I wanted to present is our ISES infographics. We've had 2 installments now. In 2018, we had an installment of infographics called Dispelling the Myths, Renewables in the Grid. And then last year, we did a second installment on solar thermal heat for industry processes. But just as an example, in the first installment, we approached the question of the solar resource forecasting and how predictable the solar resource is in terms of dispelling myths about the about the inability of integrating variable renewable energy into a grid. And so I encourage you to go look at our infographics, especially for those of you interested in solar forecasting, the one we produced back in 2018. And of course, your feedback is always welcome on these. And that's really the crux of our webinar today, is to talk about late developments in the area of solar resource forecasting, especially to support utilities and managing the variability of the solar resource in their grid operations that have large amounts of solar PV. This is a topic that has been taken up by the International Energy Agency Photovoltaic Power Systems program. It's now called Task 16. And what I would like to do is first introduce the operating agent for Task 16, Jan Remund. Jan is studied geography at the ETH Zurich and is the head of the business unit of solar energy and climatology at Meteotest since 1993. And he became the operating agent of this PVPS task a couple of years ago after the task completed its earlier work under the solar heating and cooling program. Back then it was called Task 46. But this is an ongoing program of experts from around the world working in solar resource, all aspects of solar resource assessment issues. So Jan, I'll turn the webinar over to you, and you can give us a brief update on what's going on in Task 16, and then we can go right into our specific talks on the solar resource forecasting issues.
Yes, thank you very much for the introduction, Dave. Thank you to ISES to have this organized. As Dave said, I'm the operating agent, the project lead, the organizer of this Task 16, and I will give you in the next few minutes a very short overview of this task before we start then with the individual talks about the forecast issues. PVPS, it was shortly said, it's a program which runs a long time. I think the main thing is the real good idea that sustainability starts with global collaboration. So it is that we try to work together globally to get the best out of the knowledge, to spread the knowledge all around the world. Okay, let's go on. So PVPS, and we try to work to strengthen our collaborative works to facilitate solar energy and photovoltaic and make it the cornerstone of the energy transition. Who is part of this? So there are universities, research organizations, med services, service providers are part of this. There are 55 organizations throughout 21 countries. It's more or less worldwide, the coverage, aside southern part of Africa and Asia, which doesn't take part at the moment. Why we need still to have such a solar task? The first solar task, it started in the end of the 70s already. So the solar resources are the fuel of the PV, CSP, and solar thermal energy. So we are also still linked to the other TCPs, SHC and solar PACEs. PV gets bigger and bigger, the installations, the penetration gets higher. Those facts induce that we need finer spatial and temporal solutions and a higher, less uncertainty, because uncertainty means higher costs. We more, as added value, we will make, or we are doing benchmarks. We are describing the state of the art. And finally, our final aim is to lower the uncertainties, which leads to lower costs of implementation, and therefore also to more photovoltaics. We have divided our work into 4 subtasks, as it is done normally in such programs. The first one is dealing with resources and models. That's the more scientific part. We are looking at the measurements of the ground, but mainly about the global radiation, but also about soiling and spectral data. We are looking at numerical weather prediction and satellite-based data and building up a benchmark framework. This is led by Manojit Sengupta from NREL USA and Stefan Wilbert from the German Aerospace Center from Germany. Subtask 2 is about solar source data. This is not the scientific part, but the part seen by the customers. They want to describe the available products to give them guidelines. We are defining the data quality and formats, looking at the long-term variabilities, looking at also at PV at urban scale, so like solar cadastres, how to do this best, but also looking at the bifacial modules, or not at the technology, but here we try to enhance the basic information which is needed, which is mainly the albedo. This is led by Philippe Blanc from Mine Paritech from France. The third one is about forecasting, and this webinar is dealing with this subtask. Here we are looking at the regional solar power forecasting, for example, for distribution system operators. We are looking at probabilistic forecasting, at all-sky imager-based forecasts, and also looking at firm PV power. This is led by Elke Florenz from Fraunhofer ISE and Carmen Köhler from P3R Solutions Germany. As I said today, today's topics is based in this subtask 3. The last one is the dissemination. This webinar is also part of it. We are making webinars, workshops, writing reports. We just published one lately about the regional solar power forecasting, where different methods to do this are compared and the best options are described. This is led by myself, this subtask. The outlook is, so we are now in the second phase of our task. It goes for another 3 years, and we are working hard now on finalizing the result of the first 3 years. This will be the update of the Solar Resource Handbook, which is published up to now by NREL and will be also published by NREL again, and we will publish this by the end of this year. Thank you for your attention.
Thank you very much, Jan, for that very concise and thorough overview of Task 16, of our PVPS Task 16. So now let's go right into some of these subtask presentations, the subtask 3 presentations that Jan mentioned in the solar forecasting area. Our first speaker today is going to be Lennard Visser, who is a PhD candidate at the Copernicus Institute of Sustainable Development at Utrecht University in the Netherlands. His PhD is investigating short-term variability of solar power generation and models for short-term solar power forecasting, and in particular, he's focusing on day-ahead models for single or aggregated PV systems at a regional level. And he will talk to us today about benchmark analysis of day-ahead solar power forecasting techniques using weather predictions. So, Lennard, the podium is yours.
Thank you, Dave, for the kind introduction. Just opening the presentation now. Hope you can see it well. So this study was about a comparison between different models that forecast the day-ahead power production of a PV system and aggregated PV systems. And for this study, we used weather predictions as an input. So to continue directly into more depth, so one of the most important reasons why we're interested in day-ahead forecasting is because most electricity is traded on day-ahead market. And because of that, the dispatch of power generation or the power plants is mostly decided upon this time horizon. So in order for solar power to become a major part of our electricity system or generation in our system, it's important to have reliable and accurate forecast of the next day power output. And therefore this topic is very important to also important for grid operators to manage their balancing capacity. So how does it work, the day-ahead market? So basically every day a bid is submitted to the spot market, usually depending on the market a bit, but usually around noon. And this bid holds a volume and price for every trading block of the next day. So because of the structure of this spot market, we need forecast with a lead time of about 12 hours and a time horizon of 24 hours, because we need to forecast the entire production for the entire next day. So in solar forecasting, we have a few different techniques, but since you're interested in day-ahead forecast, there are actually two techniques that are valuable to apply. First one is numerical weather predictions, and these are basically the weather forecast as we all know it for many years already. The second one is statistical learning, and these include models that, for example, forecast the PV power production based on a number of input variables. And these include both machine learning models as well as regression models. However, in more recent work on solar forecasting, we actually find that the combination of these two models generated best performance results. And that's also what we looked into in this study. So what we basically did is that we used the numerical weather predictions as an input to the statistical models. And therewith we generated the hybrid model. You can also place it the other way around and mention that the statistical models are used to post-process the numerical weather predictions. So in this study, we use the NWP forecast to generate PV power predictions for single PV systems on a day-ahead basis, but we also looked into the value of aggregating multiple systems, which are spread throughout the region. So the region that we considered and the PV systems we considered in this work are all from the UP network. This is a network of about 200 systems, which has been monitored for about 4 years in Utrecht, which is a province within the Netherlands. And because only data for a longer period is available for 152 systems, these are the systems that we have selected for the study only. So to continue to the methods, as I mentioned before, we use numerical weather prediction as an input to the statistical models we consider. And these variables that we have extracted all come from the European Center for Medium Range Weather Forecast and include variables like the total precipitation, the predicted solar radiance, cloud cover, pressure, temperature, and a few more. In addition to that, we used a couple of other variables like the clear sky radiance, the solar zenith angle, month of the year, and the hour in the day. And we use these variables as the input to the models. But before we do so, we first standardize the variables. And this is an important step to take when considering a few of the models, like neural networks, because it turns the input variables in the same order of value, which helps these models to reach the best performance possible. So thereafter, we can now insert the variables into the models, and the models that we consider in the study were small persistence, which is persistence based on the clear sky index, a linear regression model, a lasso regression model, a support vector machine with a linear kernel and one with a radial basis function as a kernel, a random forest model, a gradient boosting, and finally a neural network. However, before we can produce these predictions on a day-ahead basis, we first need to initialize and also train the models. And we do this considering 2 entire years of data. But since we need, or we want to make the predictions as well as the errors independent of the system sizes of the PV systems, we first normalize the PV power measurements. And then thereafter, we can finally produce the forecast. And after the forecasts are generated, we remove the outliers. And then we evaluate the output based on the mean absolute error and the skill score. And in this study, the skill score was based on a root mean square error and the small persistence model, as already briefly mentioned before. So to get an idea of what these forecasts look like, here we see in orange 4 different days for one single PV system. And in addition to that, we see the predicted power output of 2 different models. So when we consider the entire year, here you see 2 box plots holding the mean absolute error of all the 152 systems we have considered. And this first plot shows the mean absolute error, but the second plot shows the skill score. And before I continue, it's important to mention that the higher the skill score, the better the model works. So according to these box plots, we see that all the statistical models we have included in the study outperform the smart persistence model, which is a common benchmark method in solar forecasting. I should have mentioned that before. But in addition, we also see that slightly more complex models like the neural network or the random forest model outperform the linear models we have selected in the study. So if you look a bit more into detail, we find that random forest achieves the best performance in terms of the mean absolute error, while gradient boosting outperforms the others in the terms of the skill score. So after we considered the forecasting of a single PV system, we now want to evaluate the value of aggregating multiple systems throughout the region. And we did this by randomly sampling multiple systems. So in this plot, we see the results for 3 different models I've selected. And we can also evaluate to what extent the model prediction improves as the number of sites increases. And what we see here is a couple of things. So the improvement of the statistical models is more significant than the smart persistence models. But we also see that when we evaluate all the statistical models, the improvement is relatively similar. Secondly, we see that the rate of improvement decreases as the number of sites increase. And we also find that the deviation or the differences between the errors from one subgroup to another decreases as the number of sites increase. So if you consider all the models now and 150 PV systems in total, we still find random forest we still find that random forest achieves the best performance compared to the other models. And in terms of the skill score, we now see that the kernel support factor machine, or the one that has a radial basis function as a kernel, is outperforming the others in terms of the skill score. What's similar to the evaluation of a single PV system is that the smart persistence model is still outperformed by all the other models. And again, the more complex statistical models outperform the linear models. So to conclude, in this study, we compared different statistical models that are commonly used for PV power production on a day-ahead basis. And we found for both single and aggregated PV systems that the more complex models outperform the others. For single PV system forecasting, we saw that random forest and gradient boosting achieved the best performance. But when we considered the aggregated systems, we found that kernel support factor machine beats the gradient boosting models. With this, I would like to conclude my presentation. If you have any questions, feel free to ask me during the Q&A later this afternoon, or send me an email. Thank you very much.
Thank you very much, Lennard, for your very interesting talk and for the interesting work you're doing towards your PhD. I'm sure we're all going to be very interested in following this as it progresses. Our next speaker, next expert on the solar resource subtask work that's done under PVPS Task 16 is Dennis Vandermeer. Dennis has a bachelor's degree in mechanical engineering and a master's degree in sustainable energy technology from Delft University of Technology in the Netherlands. And since 2016, he's been a PhD candidate at Uppsala University, where he's developing probabilistic forecasting methods for solar power and electricity usage. Here he's going to discuss a presentation titled Space-Time Trajectories from Probabilistic Solar Forecasts. So Dennis, welcome to the podium.
Hi Dave, thank you very much. Let me just put up my presentation. All right, can you see my presentation now, or do you see also the notes?
We also see the notes.
Okay, then I will do it like this.
Perfect.
All right, Dave, thank you very much for your kind introduction. So yeah, like Dave said, my name is Dennis Vandermeer, and I will talk today about a recent study that we published, where we tried to generate space-time trajectories from probabilistic solar forecasts. So the outline of today's presentation: first, I will talk a little bit about what space-time trajectories actually are, why we need them, how we can generate them, and then how we can generate them specifically from probabilistic forecasts. And then I will say a few short words about probabilistic and multivariate forecast assessment. And then I will continue with the results and finally conclude this presentation. So space-time trajectories are actually constantly being issued by meteorological institutions. Lennard showed also an example in the previous presentation already. So here we see, for example, a temperature time trajectory by the 10 ensemble members from the Met Co-op ensemble prediction system at a single grid point in space. So basically this is a time trajectory, if you will. So why do we need space-time trajectories then? Well, it is because the spatiotemporal dependent structure provides useful information to operational decision problems. For instance, the electricity market participation. We might be interested in certain zones where there is additional PV or wind production. The same goes for power system reserve quantification. It is also interesting to use trajectories in stochastic model predictive control, where we want to have trajectories that contain the optimal correlation structures so that we can make well-informed decisions. And of course, probabilistic power flow simulations, where we can determine where there will be hotspots in the feeders, for example. So there are many ways to generate space-time trajectories from probabilistic forecasts. So in the previous presentation, Lennard showed one way of doing it, actually. So that's very nice, so that I don't have to explain that anymore. But we are mainly focusing on space-time trajectories from probabilistic forecasts. And the common way to issue a probabilistic forecast is by quantile regression. Basically, that is saying we issue a quantile forecast with a certain nominal probability level tau, which is in fact a part of an inverse discrete cumulative distribution function, or a CDF. And by choosing certain nominal probability levels tau, for example, I chose here 0.30, 0.10, 0.30 up to 0.90, it's possible to issue a discrete inverse CDF, as you see here in the figure. What you see here on the vertical axis is the cumulative probability, and then on the horizontal axis we see the irradiance forecast, in this case, in watts per square meters, with the different quantile forecasts. So the next step is then, now that we have our predictive cumulative distribution function, is to generate trajectories from that. And that we can do by drawing a random number from a standard uniform distribution and interpolation, basically. That looks like this. So let's say we draw 0.82 from our standard uniform distribution. Then we find that our trajectory at one point in time and one point in space would be 865.4 watts per square meters. And this is known as the inverse probability integral transform, or also sometimes called as inverse transform sampling. And I think there are some other names as well. But we are, of course, interested in space-time trajectories. So we look at, for example, Z locations and K forecast horizons. Then we need D random numbers in total in order to generate one space-time trajectory. So if we do that many times, we can generate a whole bunch of space-time trajectories. Now, it's important that these uniform random numbers actually represent the spatiotemporal correlation. So I've just chosen a purely temporal example because it's just so much easier to present, where we have 5 random samples of length k for the forecast horizon. And as you can see, there is complete randomness. So if we push this through our probabilistic forecasts, we see that our scenarios in red show much higher variability than the data in green actually contains. So the issue here is that we need to somehow generate these uniform random numbers with the correct autocorrelation, such as this. And then when we push these through random numbers through the probabilistic forecast, we'll see that we actually generate scenarios or trajectories that have variability that is very similar to that of the data. Now, in this case, we used copulas, and we compared copulas, in fact, to model the spatial temporal dependent structure and to sample correlated random numbers from it. So just a short background into copulas. So let's say that we have the random variables x, all with cumulative distribution functions. And then there is a theorem by Sklar stating that each multivariate CDF can be expressed by its marginals and the copula C. And what makes this very appealing is that we can model the dependent structure and the marginals separately. And in this case, as you can see, what's also interesting is that the marginals are uniform here. So this means that we can actually sample random uniform numbers in D dimensions and use the inverse probability integral transform to generate space-time trajectories. All right, so we use data from the Oahu parameter network on Hawaii, which has 17 locations in total. And we looked at a total of 9 forecast horizons. So that means that the total dimension the problem is 153. And on the right, you'll see the flowchart that represents how you would approach such a problem, which is very similar to how you would approach a normal forecasting problem, where you use an offline data set to select potential candidates. You evaluate them along with using some criteria, and you choose the best one that you use in your online setting. Just a few words on assessment. So probabilistic and multivariate forecasts should be calibrated so that we don't have any biases in our decision-making processes, for example. And one way of evaluating probabilistic forecasts is a rank histogram. And this one should be flat in order for the forecast to be calibrated. But the problem is, of course, that we don't have just one dimension. We have now D dimensions. So there is a lot of research ongoing in the atmospheric sciences to deal with this issue. And one of the solutions is so-called pre-rank functions that have been proposed in the literature. And it's important to note that none of these rank histograms individually are able to detect all types of miscalibration, so biases, dispersion issues, but also problems with the dependent structure in the trajectories. So that's why we chose the average rank and the band depth rank histogram in this case. Yeah, and this is just to illustrate what the problem is. So on the right, we have the traditional problem, the univariate prediction, and then on the left, we have the D-dimensional prediction. All right, so then I come to the results of our study. So basically what we see here is the various results from the various copulas that we tested. So on the right, you will see 4 copulas. In the first three are the so-called parametric copulas, and the empirical copula is the non-parametric. And the rows here indicate the the rows indicate here the average rank histogram, ARH, and the band depth rank histogram, BDH. And so in this case, we can see that the Gaussian copula does not appear to be flexible enough to model the spatial temporal dependent structure. Similarly, the student T, the student T copula results in too high correlation or under dispersed trajectories. And that's mainly because of figure F that we can see that, because actually if we look at figure B, we might be tricked into thinking that, well, there is actually quite proper calibration for these space-time trajectories. And this is also the reason why it's common to use several of these rank histograms so that we are not misled by the deficiencies of any single rank histogram. And coming to the Clayton copula, in this case, it's completely inconclusive, actually, what type of miscalibration causes these rank histograms. But what we can be pretty sure of is that the calibration overall is quite poor. And this is probably because the Clayton copula is parameterized by a single parameter. And then finally, we see that the empirical copula produced slightly under-dispersed trajectories, which we can deduce from figure H. But it should be noted that this is also partly due to the probabilistic forecasts, which were slightly under-dispersed. So there are a lot of extra dimensions when evaluating multivariate forecasts or space-time trajectories. So then we've arrived to the conclusions. So I started out by saying, why space-time trajectories are an important input to decision-making processes. It's because the spatial-temporal relationship contains valuable information. I explained a little bit about how space-time trajectories can be created through several techniques, and actually Lennard also showed that for me already. But we focused on probabilistic forecasts and copulas combined. And we saw that a copula is a versatile tool to model the dependent structure and the marginal distribution separately. And what we found is that parametric copulas, the Gaussian, the student T, and the Clayton copulas, in this case are not flexible enough for the relatively large number of dimensions. And that the empirical copula showed better performance, which is probably because it's non-parametric and therefore much more flexible. Thank you for your attention.
Thank you very much, Dennis, for this very interesting talk about probabilistic solar forecasting. It's you're making some very good progress, and I wish you all the best on your PhD work in this area. Just a reminder to all of our participants out there that we should have time for the panelists to respond to your questions after the conclusion of the panel speeches. So please feel free to pose your questions in the question area of your menu in the GoToMeetings menu that you see on your computer. All right, our next speaker is Dr. Richard Perez. He leads the solar energy research work at the University of Albany's Atmospheric Sciences Research. And he's also on the advisory board of the George Washington University Solar Institute. He served on multiple terms on the board of the American Solar Energy Society and is an associate editor of the Solar Energy Journal. He's well-known publisher, has over 250 journal articles, book chapters, and conference papers, and holds U.S. patents on energy storage and load management using photovoltaics. And he's been doing a lot of interesting work recently on the dispatchability of solar PV in the utility grid and on perfect forecasting. And I'm looking forward, Richard, to your presentation this morning, or today, this morning here in Colorado.
Good morning, everyone. Dave, I was supposed to go last, but I'm happy to go now. Can you see my screen?
Sorry, Should we?
No, that's fine.
Would you prefer?
That's fine. I'm happy to go.
Okay,
to go
I apologize. I wrote it down wrong, but if you'd like to wait until after Patrick's talk, that's fine. What would you prefer? Should we go with Patrick? Okay.
So can everybody see my screen? Am I sharing properly?
Yes, all good. Go ahead.
Yes, your screen is good.
So I'd like to tell you about firm solar power forecasting and showing that it's a way to ultra-high renewable penetration at least cost. And I would like to illustrate that with a case study we did for New York State. So firm forecasts. This is our forecast for tomorrow, but even the best forecasts, even with all the bells and whistles, they are not going to be perfect. Sometimes we overestimate or underestimate. But predicted output, on the other hand, could be guaranteed by adding hardware operating in tandem with the PV systems, namely storage to make up for overprediction and overbuild to make up for underpredictions. From a grid operator standpoint, they could deal with firm forecasts, even though the models themselves are not perfect. So that's my presentation plan. I'd like first to say that firm forecasts constitute interesting new metric to validate forecast models, then that it's a low-cost deployable strategies for zero uncertainty grid operations, and last but not least, that it's an effective entry to firm power generation and the ticket to ultra-high PV penetration at least cost. And I will illustrate that with a case study we did for the New York TSO. So first, the validation metric. We've heard about the standard metrics that people use, MAE, forecast skills, etc. The perfect forecast metric is how much it costs to make it perfect, how much storage you have to do and how much overbuild to make it perfect. And all you have to do is define how much you pay for PV and storage. And here we're going to look at current and future costs for those two technologies to illustrate. So let's illustrate the metric. I'm going to run the SUNY forecast model, which you'll hear later on, which is also called SolarAnywhere, which is a combination of NWPs and satellite-derived models. And I'm going to compare the SUNY and all its underlying models. First with a standard metric, the MAE in that case. So I have 3 time horizon, 1, 3, and 24 hours in 3 different colors. And you can see expected hierarchy among model, and that smart persistence degrades very rapidly. However, when I look at it with that new cost metric, now the y-axis is the cost, how much do I pay to make the forecast perfect? The hierarchy is more or less respected with one big difference. Smart persistence, to quote a former US president, is misunderestimated. In fact, it's probably the best model up to 3-4 hours time horizon in terms of operational cost. That's because it can have a lot of scatter, but scatter is either positive or negative 1 hour to the next, and at the bottom line, it costs not all that much to make it perfect. So that's a new interesting twist in forecast. So when we look at scale, if I look the firm forecast metric, there is all the scales are negative. If I look at MAE, all the scales are positive. So that's a new dimension to when you talk economics. Now, if I look in the future and I look at an extended fleet over, say, an entire state like California, I can see that cost to make the forecast perfect is not very high. So you could actually operate fleets of PVs, doing away with all forecasts and uncertainties, delivering firm forecasts to the power grid, and have kind of zero uncertainty PV fleet operations. So removing all the aspects of probability and everything. Utilities can count on what you predict with 100% certainty if they pay a small price. The most important, however, is that same firm forecast approach using storage and overbuild is also the ticket to much bigger vision, which is 100% PV, firm, dispatchable, available night and day, 365 days a year. So that's the way it works. I'm looking now at firm power generation. We know that intermittent, and I have a y-axis here showing the cost, the LCOE of generating electricity. So intermittent PV is very cheap. It's probably the cheapest way to make electricity today. But if I'm going to firm it up, making it available 24 hours a day, 365 days a year with absolute certainty, it's hopelessly expensive, even if I use the lowest projection for storage in the future, unless I apply overbuilding and curtailment optimally. And when I do that, something interesting happens. That white line is the firm power LCOE, and there is a point where it can approach grid parity, at least in the foreseeable future, where you can think of that PV producing electricity nonstop all the time. And we just finished a major study for the central US, the mid-continent independent system operator, where an optimum mix of PV, wind, with a slight residual component of gas can lead to less than 5 cents per kilowatt hour generation without even counting on any benefits. That's straight business cost. So that overbuild and curtailment approach is so effective that we started calling it, in fact, implicit storage, because it does the same thing as storage. It makes storage much cheaper, in fact. It's a catalyst to storage. So this is the logistics of firm forecast. So the duty cycle is to transform the forecast, the actual production in yellow, into what we predicted in black. So that's the job of storage and overbuild to do that. But it's not all that different, although the job is much bigger to do the 100% logistics. In that case, it's transforming the actual PV into the load shape. But that can be done with exactly the same strategy. So now I'm going to illustrate that in the case of New York. That's the New York State, where I live. New York ISO is 32 gigawatts, so it's not very large, but it's not small either. Has 11 electrical regions, and we're going to look at single plants in each region, as well as homogeneously dispersed fleets throughout each region. And we're also going to look at the entire state operating as one, and at different levels of flexibility from 0% to 5%. For grid penetration, we are going to start at near zero, where the order of the day is to provide firm forecasts, and increasing that penetration all the way to 100% when the order of the day will be firm power generation. And that's how things evolve. We start with the forecast duty cycle, which is you have to generate the load shape that you predicted. On the right, I have the daily load shape, and on the left, I have the yearly load shape. And as I penetrate, that load shape morphs step by step as a function of penetration into the actual load shape. So the job becomes much harder. You have to produce at night, and on the left, you have to produce in winter, where you have a giant supply deficit. And this is what it takes in terms of storage to the left and implicit storage on the right. So we start on the left at 0% penetration, firm forecast, and to the right, 100% penetration, firm power generation. So even on the right, it's only 7 hours of storage. It's not hundreds of hours of storage. And on the right, it's overbuild. 180% overbuild will do the optimally economic job. As I increase flexibility, I can get away with much less hardware to do the job. But the most important yardstick is how much does it cost to do that. So I start with, and I compare that with the cost of unconstrained PV, where you just generate PV and don't care about when it produces. So it costs more to do perfect forecasts to the left, but not much more. And it costs a little more to do firm power generation, but not all that much more. But it's most interesting if we are going to do planning of ultra high penetration PV for the future, if we take the future costs, the ones which are expected 15, 20 years from now. So we start with a very small premium for firm forecasts to the left, and end up, if we have 5% flexibility, with an LCOE at about 5 cents per kilowatt hour in New York State, which is not bad. It's probably cheaper than what is generated today from conventional generation. But the biggest value is if I take that 5 cents per kilowatt hour, if I didn't do that strategy of optimizing storage and implicit storage, that's where I would be when I reach 100% penetration at over 50 cents per kilowatt hour, which is totally unacceptable and would be a big showstopper in the way of ultra-high PV penetration. Some interesting findings beyond this fundamental success of the approach is to look at regions. Now I look at all the electrical regions of New York State, from the smallest one, New York City, for instance, to the left, and the biggest ones to the right. So if I look at 1 hour forecast, the premium compared to unconstrained generation decreases as a function of region size, which is expected. You average the weather, you do better. We've seen that in a couple of presentations before. That advantage becomes smaller if I look at day-ahead forecasts, and it entirely disappears when I do firm power generation. So the region size hardly matters when you do high penetration, ultra-high firm generation PV. What matters a bit more is the actual solar resource, the availability of solar. Here I have a map of capacity factor in New York, so we get more sun in the south, New York City, Long Island, and the smaller regions get more sun, and they get away with a smaller premium. This is comparing the premium between doing regions individually and doing the entire state. So it's cheaper to do the entire state. But if on the x-axis, I have the forecast, the penetration level, starting from 0 penetration forecast, day-ahead forecast. So I get a big premium if I spread my resource over the state, but that premium goes down to almost 0 at high penetration. So that tells me that I don't need all that much interconnection to do firm power generation with PV. That could be almost self-contained within each region, which is very, very important for future planning, where people insist that you'll need to interconnect entire continents to do so. The evidence shows that it's not the case if you do it optimally. Same thing with single power plant versus distributed fleet generation. If you do forecasts, the premium you pay for a single plant is high, and you gain into spreading your resources. But as you penetrate and want to generate firm power generation, that premium goes very low. So it's not a huge penalty to centralize your resources within a city or within a few large power plants compared to dispersing it everywhere. So in conclusions, I've shown that firm forecasts constitute a different evaluation metric, showing different aspects of how good forecasts can be, and that the standard metrics may not tell the whole story, particularly scale. Firm forecast strategies can be economically justifiable today. It's a small premium to pay today, but the biggest value is that same strategies applying both implicit and real storage optimized constitute a very effective strategy to achieve ultra-high PV penetration at least cost, when at that point you will have to have firm power generation, because PV will have to produce all the time. The NISO case study points that at a 20 years time horizon, ultra-high penetration straight business life cycle energy costs will be 4 to 5 cents per kilowatt hour, which is very acceptable. It's about the price on the exchange today, on the day-ahead exchange today, on the average. And finally, firm power generation could be contained within each electrical region at a modest cost premium, decreasing with penetration, thus alleviating the need for major trans-regional or transcontinental grid buildup, and also enhancing local resiliency because you would not be dependent on a very far-fetched grid. So, and on this, I will thank you for your attention.
Thank you very much, Richard, for this extremely interesting talk and continuation of excellent work you've been doing the last few years. I'm sure these results are certainly good news and important information for the solar PV industry. As we know from the Paris Climate Agreement, especially if the world is to be capped at no more than 1.5%.
Did we lose you, or did I lose everybody?
Can you hear me?
I can hear you.
Okay. So as I was saying, from the Paris Climate Agreement, the challenge to cap global warming to 1.5 degrees centigrade means we really have to fully decarbonize our energy system by the middle of this century. And if we want to do it with renewables, which is the only and the best way to do it in my view, PV is going to play an extremely important role. So these types of analyses are really critical to planning how we are going to meet these climate challenges that are facing us today. And so with that, I'd like to move on to our final speaker of the day, who will also give us a further insights into the database that Richard has been working with. It's Patrick Keelin, is the lead product manager for SolarAnywhere at Clean Power Reseach, which is a corporate member of ISES. Patrick focuses on how the solar industry and utilities can make better energy-related decisions with scalable weather data and intelligent solutions. And he brings decades of experience working in the renewable energy industry, first in small hydropower development and then utility-scale solar hardware product development. He has expertise in decision analysis and resource allocation strategies. He will be talking today about SolarAnywhere, which will be on operational data services and applications from the SolarAnywhere product. He has a bachelor's degree in product design from Stanford University. So Patrick, I turn it over to you.
Great, thank you, Dave. Can you see the screen okay?
Yes, all good. Please continue.
Oh, okay, great. Well, this presentation is about translating research into operational services. So what motivates your research? Is it fame and fortune? If you're in solar resource assessment, maybe not. Many of us strive to make an impact in the energy transformation. But for research to make an impact, adoption is critical. So this presentation will outline key requirements for operational solar forecasting that are not always associated with research studies. First, a brief introduction to Clean Power Reseach. Who are we? Our mission is in advancing the energy transformation. We're a team of utility, energy, and software professionals located near Kirkland, Washington, and California. We have a suite of software products, primarily focused at integrating solar onto the grid or planning for solar. That includes PowerClerk's SolarAnywhere and WattPlan. SolarAnywhere is the solar radiance product, including forecasting, that I'll be talking about today. And we focus on making an impact in doing automated programs, bankable analyses, and engaging customers for over 2 decades. As an example of that impact, Clean Power Reseach works with all 10 of the top 10 investor-owned utilities in the United States, and we do over 10 gigawatts of operational solar forecasting and monitoring. So what is SolarAnywhere? It's an on-demand web service providing bankable solar data and intelligence. Horizons are forecast, real-time, and historical, so a continuous data set from approximately 1998 to 7 days into the future. It's used for fleet modeling and system validation, And finally, we have a partnership with Dr. Perez, who you just heard from, and the atmospheric sciences team at SUNY to take some of the latest research and incorporate that into our operational products. And that step of translating research into operational projects is, again, the focus on this brief presentation today. So what are some of the requirements for operational solar forecasting, meaning not just a research presentation or a paper that's done once, you present the conclusions? What happens when you need to take that and run it operationally? Here are some of the things: timeliness, data security, data integration, data availability, data quality, and no revisions. I'll be speaking about each of those. So first is timeliness. Forecast needs to arrive on time. Otherwise, it's not useful for making a decision. A forecast that's an hour or even 2 hours late, if it can't be relied upon, that's not. Similarly, data security. You can't have a product if there's breaches in data, and the data is being exposed in some way that can cause real issues, having nothing to do with the forecast, but more business. And data integration as well. We need to produce a forecast, but then that forecast is going to be used in some other system or so making sure that the data can be used by other systems is quite important. And obviously that's a little bit different than writing up a paper, say for IEEE, where that paper is for folks to read, but it doesn't have to be used operationally. So what are some of the solutions to that? Well, first and foremost, a team and infrastructure to be able to deliver a high availability and secure web service. That's something to consider. I'll also mention that on the data integration, we found that APIs are very powerful ways for systems to be communicating with each other. Sometimes forecasts are delivered via FTP, but that is not always reliable. Email, even less so. So we do recommend APIs when possible. Next is data availability. And the next two, data availability, data quality, I'll dive a little deeper into some of the issues here because these are so key to real world applications. So the first thing, or what do I mean by data availability? Data availability, I mean, in true forecast scenarios, you might not always have the data that you want. It may be missing or it may be delayed. An example of that is reanalysis data, for example, from reanalysis models like MERA2 or ERA5, very sophisticated models. We use those models in our operational solar irradiance historical data to be able to accurately model aerosols and some other parameters so that we can have very high quality historical irradiance estimates. But those sources have a delay of months or potentially longer, and so those can't be used in the forecast domain. You need other sources, or you need to omit that data. Next, solar plant data may or may not be available. This is critical. We've heard a lot about statistical methods or a regression that could train certain models to measure data. Well, what if that measured data isn't available? And that's pretty common. There may be some concerns about sharing the data, or simply if you have a behind-the-meter solar fleet, that data, the communications infrastructure may not exist to be able to get you the data that you really want. And so for that situation, sometimes using a model like SolarAnywhere to predict what the actuals could have been, rather than relying on the actual on-site data, can work quite well. And finally, satellite data, meaning the visible and infrared images that we get from the geosynchronous satellites. That's a key piece of technology that we use in our real-time irradiance models and also our short-term forecast models. There's a lag time from when that image is taken to when that data can be used operationally. As an example of that, here's an illustrative view of the forecast latency chain for the satellite that covers the west coast of the United States. And each of these bars represents how much time it takes from 0 when that image is finished to when the forecast can actually be delivered. There's a total lag here of about 17 minutes, but notice that the satellite image download, just acquiring the images, takes about 10 minutes of that time. And that can be somewhat frustrating, considering that latest satellites, they have 5-minute images available, and you'd like to be able to utilize those images to have the latest possible information. But 5-minute images may not be all that useful if there's a 10-minute or 17-minute lag associated with those things. These bars on top are more the processing time needed to turn that raw data into actual solar forecasts. Next is data quality. If using statistical methods, if using measured data, I can't emphasize this enough. Checking the quality of that data is absolutely critical. If you train on bad data, you're going to get a bad model. And measured data is notoriously dirty. That's just the way it is. The real world is messy. A couple things to call out. One would be hardware issues. So offline inverters, misaligned trackers, these are things that affect the output of the plant, but that may give your forecast difficulty trying to model that situation because it's highly unpredictable. Next is curtailment. That's another common scenario where you might be forecasting one output, but if the plant is mandated to curtail to another level, that can lead to an erroneous forecast. And then for met stations, measurement issues like pyranometer drift and soiling, pretty common things. And then just general bad data, time shifts, end of period versus beginning of period integration, very common stuff, but no question, this is one of the most difficult areas that we face when trying to take a statistical approach to forecasting, is that dealing with real plant data, especially in real time, in an automated way, where you have to deliver that forecast on time, is quite difficult. And there are some investigations ongoing there. So what are some solutions to this? Briefly, for data availability, one would be models robust to delayed or missing data. That's very important because that forecast must arrive regardless of what data you get. And second, automated QC if using sensor data. Finally, no revisions. If you submit a paper, you may have an opportunity, if you find a mistake, to go back and say, oh, I want to make an update. That's not the case in a forecast. Once a forecast is delivered, it's delivered. And for this, really critical is operational testing. Testing. How do you know that the forecast that you're delivering is living up to your expectations, or indeed living up to the original research that motivated it being put into the product? So operational testing is, if you're not doing operational testing, I can pretty much confirm that you're probably not getting the results that you want. The only way that you can know that you're getting a good product is by that testing. It has to be built into the product. And I'd also say that the metrics should be based on the highest quality actuals. So for this, the SolarAnywhere team is fortunate to have a database of extremely high quality historical data that then we can use. We can benchmark our forecasts against, especially in the case where plant data may not be available or may not be reliable, which happens, again, oh so commonly. So to all wrap up, here are a few of the requirements for operational solar forecasting that may or may not always be present in the research, but I'd encourage everyone to be thinking about as you're trying to improve the state of the art here. Timeliness, data security, data integration, data availability, data quality, and no revisions. And some of the things to consider as solutions are team and infrastructure to make secure web service, models, robust ability of missing data, automated QC if using sensor data, and finally, operational testing. Thank you very much.
Thank you very much, Patrick. for that very interesting overview of the operational requirements in solar forecasting. So now we have a few minutes for some questions and responses from the panelists. You can still submit your questions in the question box if you have some. And we have a couple here that I'd like to go to. The first one came in during Lennard's talk. So I would give Lennard the first opportunity to respond. But then we can open his, we can also have the other panelists weigh in as well. And the question is there historical data available comparing for a longer period forecasted PV production compared to a real PV production? For example, measured by satellite with a high resolution 1 kilometer and 1 hour detail. Lennard, do you want to address that? I hope I read it properly, or I can repeat it if it's better for you.
I'm not sure if I understood well. So the question is whether there is high quality historic data available regarding solar irradiance then.
Either solar irradiance or PV production, I guess, forecasted PV production compared to real PV production. But according to the question goes on with saying measured by satellite with a high resolution 1 kilometer 1 hour. So maybe the question is, what are some of the, I mean, what based on what your work is taking care of, what is some of the data sets that you're working, satellite derived data sets you're working with, and are also there PV, long-term PV data sets that you have available to work with?
Yeah, so I think the question exists of a couple of different questions. So firstly, the data I've been using is from numerical weather predictions, which are basically mathematical models that do use observations to generate future values of, for example, solar irradiance. And these are archived, at least part of these model runs are archived. So I think usually the model is run in case of the ECMWF. Some of these models are run 4 times a day in operational time, but I think online only 2 iterations per day are freely available. So that's what I've been using so far with respect to numerical weather predictions. If we're talking about solar PV, I'm not aware of any operational PV forecasts that are available. This really depends on the companies that generate these. I do think there are some companies that publish their forecasts online, but I'm not aware of any source you can go to. And with respect to satellite imaging, I don't have many experience in this field, so I do think some of my colleagues know more data sets, but there are definitely PV data sets with real-time measurements available online. And what I've been working with in the past was also a data set that is available for the region around Austin in the USA. But the actual source I should look for if anyone's interested in it.
Okay, thank you, Lennard. Do any of the other panelists have any further contributions about this topic, about this question?
Yeah, Richard here, I have a brief comment. So the question, as I understand it, asks whether you can use high resolution satellite data to validate forecast model if you don't have access to a bunch of measurements. And my experience is that yes, you can, especially if you're looking at fleets over regions of a few tens of kilometers. You don't get the dynamics, the short-term dynamics, but if you look at the standard metric, MAE, RMSE, and even the new forecast metric that are presented, results are almost identical between ground measurements and satellite data.
Yeah, I don't, that's a good answer. I think whether or not there are PV system data itself out there, especially a record of long-term PV system forecast results. I don't know to what extent that those kind of data are available. I know that there are people within subtask 3 of the IEA tasks that we're focusing on today that are doing some work in that area. Perhaps we can have future webinars on this topic that maybe help address that question more specifically. Are there any other comments, or should I move on here? I do want to mention that one general question we have is about whether or not the presentations can be made available to the participants after the webinar. I think Arabella, she doesn't have to answer now, but I think Arabella, if you can address that in your closing remarks, that would be helpful. I think the answer is yes, they are available. Let me see here, I'm going down my list. Another question that came in fairly early, would you recommend some literature about solar forecasting methods? I think, again, that came in around the end of Lennard's talk or Dennis's talk, but I open this up to all of the panelists, including Jan, if you have suggestions for good literature to go to on solar forecasting. Such as a book that Jan Kleisel put together recently. I think that would be one example. I think some of the work being published through the IEA task would be helpful as well. I don't know, perhaps Jan or others, if you have some further comments on that.
Yeah, we published just a report about the specific topic of this regional solar power forecast, about specific methods, but that's nevertheless a good overview. Perhaps also our handbook, which we are going to update. The current version is 3 years old. It's still quite current, but it will be updated at the end of the year. So also there you have some general overview.
Yeah, that's a good suggestion. Yeah, I would recommend going to the Task 16 website or going back to the older Task 46 data it's under the IEA Solar Heating and Cooling Program. Of course, the NREL handbook is referenced on those sites. So that's one way you can find those publications. And I believe some recent books, such as the one that Jan Kleisel edited, are also referenced there. It's a fast-moving field. Solar Energy Journal publishes many papers on this topic. So there's a lot of information coming out, quite a bit in the last few years, especially. Anybody else have a comment on that, or some new questions have come in recently for operational forecasting? Is it preferable to do it on site, that is receiving all data and doing the processing at the plant site where most measured data are generated, or remotely, which needs reception of data from the plant and then sending the results to the site? Patrick, would you be able to take that one on?
Sure. Yeah, I think that's very situation dependent. It has to be, if you think about, is this a utility scale plant that's dispatching energy storage and they're needing super low latency forecasting, then it may be preferable to do that on site. But for a day ahead application, maybe some amount of latency is acceptable. And I think also whoever the client is in that case will have a lot to say about what can be done there. I think one difficulty about doing it on site is the need to have the robust software infrastructure behind that, and some of the challenges associated with that. So it's not something that at least we see too commonly.
Thank you, Patrick. Anybody else want to comment on that? Let me go back to the previous question about the availability of data. The questioner gave us some feedback. He says, thanks for the satellite answer, but is there forecast data available for a longer period. And Lennard, perhaps you address that with the ECMWF example, but does anybody want to take on a further clarification of that, the availability of forecast data over a longer period?
I can have a brief answer to that. So the question inquires about the availability of back forecasts. We call them maybe hindcasts. So historical data of forecast to do some testing and validation. These are available to research institutions, mostly in-house. We have some. They are extremely time-consuming, space-consuming data sets because you have all the forecast horizons and all the spatial positions. So I don't think you can go somewhere and download back forecasts. Maybe you can do that from the standard producers like ECMWF and GFS. You can access those. They do archive those, but the operational product from SolarAnywhere, no, that's in-house. We have a few samples. So we keep them live up to the minute in-house, but you cannot just go grab them to do studies.
Okay, thanks, Richard. And anybody else?
Yeah, I would say, yeah, I have
go ahead,
the same opinion as Richard from the productive forecast as we do it also at MeteoTest. This is not stored automatically. You can go to the ECMWF, there the reanalysis data is available. However, this is not 100% as the same as the forecasting data because it uses the measurements and the historic data itself. But at least this is free, also compared to the ECMWF forecast, which is quite expensive. But reanalysis data are useful to some extent. Also from the US, there are some good data sets around from MERA, for example. And they are all free.
Great. Okay. Thank you, Jan. Let me move on here to another one. It would be interesting to hear the panelists' educated opinion with respect to the topic of very short-term forecasts, or also known as nowcasting. Does it make sense? Does it improve the performance in terms of ramp rate management and BESS sizing, or is it just going to be outweighed by cost decreasing and DC side oversizing, as I understood it? That was suggested by Dr. Perez. Did that, so fundamentally the question is about nowcasting, very short-term forecasting. How much does it really improve operational ramp management, that type of thing?
Well, that's the fundamental questions here. My opinion is that as we move to more and more PV and more storage available to manage that PV, the details of localized ramps and nowcast will be absorbed by the system. So I often use the analogy of a car on a gravelly road, and the suspension takes care of all the short-term stuff. But you need the bigger stuff. You need to know when to accelerate to go up a hill, but you don't have to forecast every nook and cranny in the road. The suspension, the system takes care of that.
Yeah, just adding to that, Richard, I find that result that you show that smart persistence is extremely effective in certain operational scenarios like you showed. And you know, is that considered a forecast? Well, there's some processing associated with it, right? But using that in conjunction with the hardware in the very short term certainly makes sense. I think also about the challenges associated with using measured data or on-site hardware between the data quality, the data lags, needing to capture, you know, every inverter outage or issue that can arise, and in the real plant, those things are quite difficult to predict. There's a lot that goes into that compared to something like a smart persistence. So, I'm sure, again, it'll depend on the situation. What's the incentives for the operation of the plant? What's the off-taker agreement and so on. But I tend to agree with you, Richard.
Yeah, I would like to make a comment as well. I think in general, I agree with both of you. It's tough to predict what it will be looking like in the future, and I think it's very much up to grid operators how important nowcasting will be. But I think what's definitely an interesting application is, for example, smaller grids like islands that highly rely on solar power. So that's definitely a valuable application for those operators in these islands.
Okay, and here's a question that's probably somewhat related to what we just talked about. It's actually two questions. First, can any of the models be used to forecast power output for every 15 minutes for a particular site? And are validation studies that are available for such forecasts? And have the models actually been used for power dispatches?
Yes, I can comment. I can comment a bit on this. So the study that I presented is actually minute resolution. So yes, there are definitely studies out there in the literature that work on higher resolution than just than hourly, for example. What was the second question again? Was about if there are any applications in power dispatch.
For actual power dispatches, yes. Power dispatching.
Yeah, exactly. So I want, maybe if there is in an operational sense, like we saw with SolarAnywhere, I'm not really familiar with that part, but we are, for example, also doing studies where we use forecasts in power systems analysis. So, for example, for power flow simulations or for model predictive control, where we want to control battery. But these are not yet operational, so it's a purely simulation-based. These are simulation-based studies.
This is Patrick. I'll add into that. SolarAnywhere offers forecasts and 15-minute resolution, hourly resolution, and then for a short time horizon, down to 1 minute based on the cloud motion vectors. So that is available. In terms of using those forecasts for dispatch, it's I'd say it's very early. We have a number of customers and projects looking at that, but mostly in the pilot stage of things, as I understand.
Great. Okay. Thank you, Patrick. Any other comments on that set of questions? I have another one here for Lennard. He talked about using exogenous inputs in its forecasting models. What kind of exogenous inputs did you use?
Yeah, so thank you, Dave, for the question. The variables that I use as an input are all available in the presentation, which will be shared, but I can also shortly go back to them. So what I use is the mean sea level pressure. I use the surface temperature or the ambient temperature and the dew point temperature. I use the wind factors, the solar irradiance, cloud cover at different altitudes, precipitation, and then the ones I also mentioned in the presentations, the clear sky radiance, solar zenith angle, month and hour. And for the variables that come from the ECMWF, these concern all predictions into the future.
Great, thank you. And one last question, and then we'll turn it back over to Arabella. I hope I can phrase this properly, but here comes a question. Well, it could be a very philosophical response to it, but how will strong programs for carbon dioxide removal, which probably mean using a lot of biomass, how will these programs impact solar forecasting activities?
Can you repeat the question, Dave?
Yeah, I'll repeat it. I'm trying to paraphrase it here, and maybe the questioner could send another comment if I'm not paraphrasing it right. But there are programs for carbon dioxide removal from the atmosphere, which probably mean using biomass. I'm not. I presume that means biochar or something like that. But how would these impact, or will these even impact solar forecasting activities? I presume this is implying that if we can remove carbon from the atmosphere through other means, then perhaps the solar industry will not have as much deployment as we're currently anticipating.
That's a good answer, Dave.
Yeah, but currently, I mean, my personal feeling is that we're on a track to continue the solar growth for the next 20 to 30 years at least a 10% annual growth rate, which is going to get us into very, very high penetration levels, which means that, in my view, solar forecasts are still going to be required unless we ultimately adopt the tools that Richard Perez articulated very well. So I think carbon capture and storage programs will, they're so far have not been very cost effective, and I know that there's still being a lot of research being done on it, but I think nevertheless, the actual market trends indicate that we're going to be needing solar forecasts for the years to come. If anybody else wants to comment, that's fine. Or if I didn't address the question properly, the questioner can send me a note. Otherwise, I think at this stage, we probably should close out the webinar after some final comments from Arabella. I think another question came in about the availability of the talks and of the recording of this webinar and the presentation. So maybe you can address that in your closing comments. So I'll turn it over to Arabella, and thanks everybody for your participation and your great questions, and also thank you for the excellent presentations from all of our panelists on this very important topic, which is continuing to get a lot of attention and ongoing research. And I look forward in the future for further ISES webinars on this topic. So thank you again for your participation. Now it's back to Arabella.
Yes, thank you very much to everybody, the presenters, and Dave as our moderator for today, for joining us, and of course also for you, the audience, for joining us today. Now, before we end the webinar, for all, as Dave mentioned, there always are questions about how to go further with this webinar, and I will be happy to address them in a second. Here. So yes, the webinar is being recorded as we speak, and this recording as well as the presentations, they are available in a few days online on the ISES homepage, so you can check them out there. For our ISES members, please remember you already have the full access to all the past ISES webinars and all the past presentations in the ISES members area, so that's also a feature that's always worthwhile checking out again. So yeah, presentations and recording will be available online. And now, before we close off for today, there's one more important announcement I'd like to go into quickly, and that is an important ISES event that's coming up just next week. That is the Eurosun 2020, the 13th International Conference on Solar Energy for Buildings and Industry. And the topic which we so well covered today in this webinar will also be amongst the conference themes. So this is going to start actually next Tuesday, so we are just a few days out. Registration is open at eurosun2020.org. You can still join us, and ISES members benefit from their ISES members discount code. So we are very much looking forward to this first ever virtual Eurosun, which is a completely new experience to us as well. And yeah, so we hope many of you are going to join us today, next week, sorry. And now, on behalf of ISES, we thank all of you, and of course, again, the speakers and our moderator for joining us and participating in the Q&A. We are always looking forward for your feedback, so you can write to us at public.relations@ises.org, and we invite you to complete the survey, which you will receive as a follow-up to this webinar. Also, remember, you have now a 20% discount code coming your way to join ISES as a member, so we are looking forward to hearing from you on this as well. So thank you to everybody who joined us today. We will now end the webinar, and we wish you a great day around the world, wherever you are. Goodbye.